Hello everyone, welcome back to another episode of Solving LEETCODE questions. Today's question is surrounded regions. The question is as follows. You're given an n by n matrix board containing letters X and O. The goal is to capture regions that are surrounded. Here are the definitions. A cell is called connected to adjacent cells if they're connected horizontally or vertically. To form a region, connect every O cell. And the region is defined to be surrounded with X cells if you can connect the region with X cells and none of the region cells are on the edge of the board. Once we find such regions, we capture it by replacing all the O's with X's in place within the original board. Let's look at the example below. Here we have a region in the middle of the board because it's surrounded by X's and none of the O's touch the edge of the board. As a result, we can capture it by replacing the O's with X's. However, the O on the last row cannot be captured because it's at the edge of the board, so it's not surrounded. How do we solve this question? Pause here if you'd like to think independently for a moment. The key here is that we can replace all regions except the ones that touch the border of the board. In other words, regions with O's at the border cannot be captured. Therefore, we just need to focus on the border of the board and find all the regions that touch the border. We know that those regions cannot be replaced, and all the other O's can be changed to X's. To summarize, here's what we'll do. We'll check every cell on the border. If it's an O, we find the largest region that includes this cell. And we mark all the cells in the region immutable. Let's mark it the letter K. In the end, we know that the other O cells can be replaced by X's, but the cells marked as K needs to be kept as O. So we change the K's to O's. Now that we have the overall steps, let's dive deeper and think about how we can find a region. The definition of a region is a cluster of cells that are connected horizontally and vertically to one another. This means that at the current cell, we need to look up, down, left, right, all four directions to see if the region can be expanded. This reduces the problem to a searching algorithm. In this video, we use the depth-first search approach. As a reminder, depth-first search is the algorithm to search as far as possible along one branch before backtracking and explore the other branches. So let's get started. The idea is that we want to change the cell to a K if it meets certain conditions, and we'll proceed to the next cell in all four directions until the conditions no longer satisfy. So when do we know it's time to stop? Well, when we're moving outside of the board, or when the current cell is no longer an O. That's when we know we've explored as far as we could. So we finish exploring this branch. Otherwise, we set the cell to K and we move on to the next position. And that's how you implement the depth-first search. Putting everything together, here's the pseudocode in Python. For every cell on the top row and bottom row, we perform depth-first search to find all the regions with O's and replace them to the letter K because we want to keep them. And we do the same thing for the leftmost column and the rightmost column. In the end, if the cell is marked as the letter K, we change it back to O, and all the other cells can be changed to X's. The final time complexity is O of n by n because at most we'll traverse every cell in the board, which is m times n cells. And the space complexity is O of 1 because we're modifying the board in place. And this is the complete solution to this problem. As mentioned earlier, this is not the only solution. We can also perform other search algorithms such as breadth-first search. This method explores all branches one layer at a time. If you're interested, try it out and let me know the solutions in the comments. That's it for today. Thank you for watching and see you next time.